Then after the topic, that is force between two parallel currents and the definition of ampere current. Now see here, if two conductors which are parallel and both are carrying current, then they exert the magnetic force on each other. Scientist Ampere studied this thing. Okay. Now, here we have to derive the equation for the force between two parallel currents. And then we will understand this thing. In which condition they attract each other and in which condition they repel each other. Now see, suppose as shown in the figure, we have two conducting wires A and B, which are parallel to each other and separated by distance D, and both are along the x-axis. Now, the wire A is carrying current IA and wire B is carrying current IB. Okay. Now see here. Suppose first we think about the magnetic field of wire A, which one is carrying current IA at perpendicular distance D from the wire. Then in previous theory, we already studied this thing. Magnetic field of A, that we can write mu 0 IA upon 2 pi D. Now, here, what will be the direction of this magnetic field? So, from right hand thumb rule, we can understand this thing. This magnetic field of wire A at the position of wire B, that will be perpendicular to the plane of paper going inside. So here it is represented by crosses. Now we can say this thing. Here the situation is this one. The current carrying wire B is in the magnetic field produced by current carrying wire A. And previously we studied this thing. If any current carrying conductor is placed in the magnetic field, the force acts on it. Now see, in the magnetic field of A, the current carrying wire B is placed. So the force on L length of wire B carrying current IB. So here, if we consider length L, then its current element, that will be IB into L. And if IB into L is in the magnetic field BA, then the force on it, that is IB cross B, IBL cross BA. Magnitude wise, we can write IBL into BA into sine theta. But IBL, that is in X direction, and your magnetic field BA, that is perpendicular to the plane of paper going inside. So theta is 90. So you can write now force on B by A, that is IB L BA sine 90. So IB L BA, that is mu 0 IA upon 2 pi D sine 90, that is 1. Now, we can write therefore force on B by A, that is mu 0 IA IB upon 2 pi D into L. If we take this length L on left hand side, then we will get the force per unit length of the wire. small FBA, that is capital FBA upon L mu 0 IA IB upon 2 pi D. So if two parallel currents are there, then the force between those currents per unit length of the conductor, that is mu 0 IA IB upon 2 pi D, where D, that is the separation between those two. Clear to all of you? Now here, if we consider the force on B by A, or if we consider force on A by B, no doubt magnitude wise both the forces will be same one, but direction wise it is opposite. Now here in text it is given to you, if the currents are parallel, then there will be the attractive force between those two. And if currents are in opposite direction, anti-parallel, then they will repel each other. Later on, we will prove this thing. Clear to all of you? Now see here, as shown in the figure, this is X direction, this is Y direction. So Z direction, that is perpendicular to the plane of paper and outward, that is Z direction. Now magnetic field of current carrying wire A. So this is wire A, wire B is below it. So if we hold this wire A in the right hand like this, thumb is in the direction of the current, then from the lower side, the fingers are going inside like this. See, from lower side, the fingers are going inside. So here at the position of B, the magnetic field is going inside. So direction is perpendicular to the plane of paper going inside. So that is negative Z direction. That is negative Z direction. So this particular magnetic field produced by current carrying wire A, that is in negative Z direction. So we can represent it in the vector form as vector BA equal to mu 0 IA upon 2 pi D into minus K cap. Now, force on the current element IL in magnetic field BA. So that is F equal to vector IL cross vector BA. Okay. Now, IL, that is in X direction, and your BA, that is in the vector form, this one. So substitute here IL, which is in X direction, that is I caret, cross mu 0 IA upon 2 pi D into minus K caret. Clear up to this one? So we can write now mu 0 IA IB upon 2 pi D into minus I cross K. But I cross K, that is minus J. So we can write mu 0 IA IB upon 2 pi D into bracket minus minus J cap L as it is. So the force, that is mu 0 IA IB upon 2 pi D J caret into L. So this is the force on B by A. And C, it is in positive Y direction. So wire B is below wire A. And on B, the force that is in upward direction means A is attracting B. So here now we can conclude like this. If the currents are parallel, then they attract each other. So, if currents are anti-parallel, then they will repel each other. Clear to all of you? See, the definition of 1 ampere current was given by scientist Ampere using this equation of the force acting per unit length of the parallel or anti-parallel currents in the conductor, which are separated by distance d. See here, suppose first we consider current IA and IB both are 1 ampere, and the separation between those two conductors carrying these currents, that is also 1 meter. And then if we substitute the values here, then current per unit length of the conductor, that is mu 0 4 pi into 10 raised to minus 7 IA1 IB1 upon 2 pi d, that is 1 meter. And if we solve this one, then we will get the force per unit length, that is 2 into 10 raised to minus 7. Now from this one, this calculation, the definition of 1 ampere current, that is given like this. Now see here, the ampere is the value of that steady current, which when maintained in each of the two very long straight parallel conductors of negligible cross section and placed 1 meter apart in vacuum, would produce on each of these conductors a force equal to 2 into 10 raised to minus 7 Newton per meter of length. Then that is 1 ampere current. Or in other words, we can say if in two long parallel thin wires, the identical currents are maintained, which are separated by 1 meter distance. If the force per unit length of the wire is equal to 2 into 10 raised to minus 7 Newton per meter, then we can say the currents in the wire, that is 1 ampere in each. Clear? Now 1 coulomb charge that we can define in terms of ampere. When a steady current 1 ampere is set up in a conductor, the quantity of the charge that flows through its cross section in 1 second, that is 1 coulomb. Clear to all of you?